When the turbofan first took over from early turbojets in the 1960s, it revolutionized flight. Covering the fan in a nacelle and pushing most of the air around the engine core made airliners both quieter and more efficient, and that design still powers almost every jet today. But Airbus and CFM International are now testing something that looks nothing like the engines you see at the gate. Their open rotor concept strips away the nacelle entirely, leaving huge composite blades spinning in the open air. The goal is to cut fuel burn by about 20%, made possible by blades that push far more air around the engine core than today's turbofan. In this video, we'll cover how the system works, where testing stands, and what could decide its future. In March, Airbus confirmed that it is formally studying an open rotor, or open fan, engine as a candidate for its next single-aisle program. The work is being carried out with CFM International, the joint venture between General Electric Aerospace and Safran, and it represents one of the boldest propulsion studies in decades. The concept moves beyond the familiar turbofan by stripping away the nacelle around the front fan, letting the blades turn directly in the open air. The technology sits under CFM's RISE program, which was launched in 2021 to develop a portfolio of next-generation propulsion systems. RISE has become the umbrella for maturing open rotor designs, advanced materials, and hybrid electric features. CFM says it has devoted close to 2,000 engineers to the effort and has already completed around 250 tests across components, rigs, and wind tunnels. That test campaign is now moving toward large-scale validation. Subscale wind tunnel models have been exercised in France and the Netherlands to shape blade geometry and explore acoustics. Full-scale ground testing is scheduled at GE's Peebles site in Ohio and Safran's Villaroche facility near Paris. System-level validation runs are also planned at Victorville, California, where altitude and temperature conditions can be simulated. The most visible step will be flight trials on a specially modified A380 testbed in Toulouse, allowing Airbus and CFM to gather real aeroacoustic and performance data in the air. All of this activity points toward a clear decision point. If Airbus wants a new single-aisle aircraft in service by the late 2030s, it will need to lock in its engine architecture by the end of this decade. That puts intense value on the data flowing from today's test program. Each result will help determine whether the open rotor can mature fast enough to meet Airbus's schedule, or whether the company must pivot to a more conventional engine option. In industry terms, the stakes are high. The open rotor is being framed as a potential step change in efficiency for the single-aisle market, which represents the vast majority of global deliveries and emissions. If it delivers the promised 20% fuel burn reduction, Airbus would be able to launch a narrow-body aircraft with a cost advantage that Boeing could struggle to match. That in turn would give CFM an extraordinary position as the likely sole supplier of engines for that aircraft, rather than the dual-sourcing model common today. The announcement does not mean the decision is final, but it does mean the technology is now on the table in a very real way. The world's largest aircraft manufacturer and the most widely used engine partnership are investing heavily in tests that will either prove or disprove the viability of flying without a nacelle. For Airbus, this is the moment where an experimental idea becomes a potential program cornerstone. The jet engines that power today's airliners are all turbofans, and for decades the simple rule was that bigger meant better. By increasing the size of the front fan, engineers could move more air around the engine core, raising the bypass ratio and cutting fuel burn. GE's Mohammed Ali has explained that this scaling strategy is now running into diminishing returns. Larger fans mean larger nacelles, and the drag from those nacelles begins to cancel out the efficiency gains. The trend line has reached a practical ceiling. The open rotor design tries to break through that ceiling by eliminating the nacelle altogether. Without the shroud, the blades can be extended to a much greater diameter, sweeping a far larger column of air. The core itself can be smaller, which reduces the amount of hot, fuel-intensive flow needed. The combination of a small, efficient core with giant exposed composite blades allows the bypass ratio to be pushed towards 60-1. For comparison, the most advanced turbofans in service today reach about 11 or 12-1. The appeal of those numbers is obvious. CFM's messaging around its RISE program highlights a targeted 20% reduction in fuel consumption compared with the best engines flying now. That margin, if delivered, represents billions of dollars in annual savings across airline fleets. It also translates directly into lower emissions for the world's busiest aircraft type, the single-aisle jet. Single-aisle aircraft dominate global deliveries, account for the majority of passenger miles flown, and sit at the center of aviation's climate debate. An efficiency breakthrough here has far greater influence on the industry's economics and carbon profile than similar gains on wide bodies. In simple terms, this is the engine category that matters most. and any step change in fuel burn will ripple across fleet planning, ticket prices, and long-term regulatory strategies. There is also a competitive layer. If Airbus can bring an open-fan aircraft to market and prove the promised fuel savings, it would hand the company a decisive advantage over Boeing in the most contested segment of commercial aviation. Airlines typically compare two competing aircraft families before placing orders. A demonstrably more efficient option could tilt those decisions heavily toward Airbus. That leverage would extend to the supply base as well. Instead of offering two engine suppliers, as with the A320neo, Airbus could potentially make the next narrowbody a one-engine program, locking CFM into an exclusive role. At its core, the open rotor is an attempt to push bypass flow to levels that traditional turbofans cannot reach. Instead of enclosing the fan blades inside a nacelle, the blades are left exposed. They are much larger in diameter and made from lightweight composites, which allows them to move a far greater volume of air around the engine core. Most of the thrust comes not from the hot exhaust gases, but from this cold bypass air. That shift reduces the energy needed from the core and cuts overall fuel use. This approach removes one of the biggest penalties in conventional designs: the drag of the nacelle itself. With the duct gone, airflow around the fan is smoother, and engineers can design the blades to interact directly with the surrounding airstream. The result is higher propulsive efficiency, with the target being a bypass ratio close to 60:1. Current state-of-the-art turbofans top out near 12:1, which shows how ambitious this change really is. Another defining feature is the use of counter-rotating fans. In many design studies, two sets of blades turn in opposite directions. This cancels the swirl that would normally waste energy behind the first rotor, and it squeezes more usable thrust out of the same airflow. The concept has been tested before, but modern composites and digital design tools give engineers much finer control over geometry and loading than was possible in the 1980s. Noise remains the hardest obstacle. The exposed blades generate strong tonal and broadband signatures that airports and regulators will not accept unless they are reduced dramatically. Current work focuses on precision shaping of the blade tips, new damping techniques within the composites, and flow management features that redistribute wake energy. These tools, combined with advanced aeroacoustic modeling, are meant to address the very problem that doomed earlier prop fin projects. Safety questions are just as critical. With no nacelle to contain debris, engineers must account for the possibility of a blade separating in flight. Instead of relying only on engine-level containment, the design philosophy includes shielding parts of the airframe itself, strengthening structural load paths, and analyzing the dynamics of how fragments might travel. Every kilogram added for shielding must be justified against performance losses. So this is a careful trade study. What emerges is a propulsion system that looks nothing like the engines we see today, yet follows the same fundamental physics. By pulling in more cold air and reducing dependence on hot exhaust, the open rotor promises large fuel savings. But the efficiency comes with challenges in noise control, integration, and certification. Those hurdles explain why Airbus and CFM are devoting so much effort to test campaigns, data gathering, and safety analysis before committing to this design for their next single-aisle jet. CFM's open rotor effort is not an abstract concept anymore. It sits inside the broader RISE portfolio, where around 2,000 engineers are working across multiple sites. The company has already logged about 250 individual tests, ranging from component evaluations to integrated rig trials. The goal is to shrink the uncertainty before the engine ever turns a wheel on an aircraft. The first wave of work involves scale models. In wind tunnels in France and the Netherlands, engineers are sweeping through hundreds of variations in blade geometry, spacing, and orientation. Each run measures how efficiently the blades push air, but just as importantly, how much noise they generate. These sessions are essential for mapping out the aerodynamic and acoustic envelope before committing to full-size builds. Ground testing represents the next step up in complexity. Full-scale open-fan units are scheduled to be installed at GE's Peebles facility in Ohio and at Safran's Villaroche site in France. These locations allow detailed mapping of compressor behavior, propulsor efficiency, and structural dynamics. Endurance trials are also critical, since the exposed blades must demonstrate reliability over thousands of simulated flight cycles. A different type of evaluation is planned in Victorville, California. Here, the focus shifts from raw performance to operational validation. Crews will run the engines through altitude and temperature conditions, as well as partial power settings that mimic real airline usage. This helps confirm that the propulsion system behaves predictably across the full operating range. The headline milestone, though, is flight testing. Airbus has committed an A380 testbed in Toulouse to carry the demonstrator. Mounting the open fan engine on this platform allows engineers to measure not just thrust and fuel burn, but also how the vibrations, acoustics, and handling qualities interact with a full-size airframe. The A380 size provides room for instrumentation and ensures safe margins if the test engine has issues. This multi-pronged approach gives Airbus and CFM the data they need for a crucial decision point. By the end of this decade, they must choose whether the next single-aisle aircraft will fly with a canceled turbofan or with the radical open rotor. To make that call, the test campaign must narrow down blade designs, pin down noise signatures both outside and inside the cabin, and prove that safety requirements can be met without wiping out the efficiency gains. For Airbus, proving the open rotor works on a test stand is only half the challenge. The other half is figuring out where such an engine could actually sit on an aircraft. Its disc is far larger than today's turbofans, and that scale affects everything from aerodynamics to ground handling. The most obvious solution is to hang the engines under the wing, just as narrow-body aircraft have done for decades. That setup simplifies systems routing and maintenance access, but with an open rotor, the rotor diameter pushes well beyond current clearances. Airbus engineers have openly suggested that the wing itself might need to arch or gull around the engine to provide the necessary space. This would influence the wing's aerodynamics and potentially require longer landing gear to keep the blades clear of the ground. Another option under study is to move the propulsion system aft, mounting it over or near the tail. This has the advantage of placing the noise source farther from the cabin, which could improve passenger comfort. It also removes ground clearance concerns, but it introduces a different set of complications. The tail would have to absorb new structural loads, and systems such as hydraulics, electrics, and fuel routing would need to be reworked around that layout. Handling qualities could also shift, since engines so far aft change the aircraft's balance. With exposed blades, safety is central to every placement discussion. Airbus teams are modeling blade-off scenarios, asking how to shield the fuselage if a composite blade were ever to fail. Reinforcing localized sections of the structure is one option, but every extra kilogram added to the fuselage reduces the fuel savings promised by the open rotor. Engineers are weighing those trade-offs in simulations, making sure that safety margins remain high without undercutting performance. Noise inside the aircraft is another variable that depends on where the engines sit. Beyond quieting the blades at the source, Airbus is studying how vibration and sound travel through the structure and into the cabin. Layout choices, isolation mounts, and materials all play a part in keeping cabin noise at levels acceptable to passengers. Each mounting position changes how those pathways behave. These studies are not theoretical exercises. They directly determine the layout of the wing, the length of the landing gear, and the complexity of systems routing. Maintenance access and serviceability are equally important, since airlines will not accept an aircraft that saves fuel but adds hours of downtime on the ground. In effect, Airbus is running a vast trade study. Every integration choice creates ripple effects in weight, efficiency, noise, and cost. The company's task is to prove that the fuel burn gains promised by the open rotor survive those penalties. Only if the numbers balance will this engine architecture move from test stands and wind tunnels into the design of the next Airbus single aisle. Airbus may be running open rotor tests with CFM, but it is made clear that this is not the only propulsion path under review. In parallel, the company is studying two more conventional approaches: Rolls-Royce's UltraFan program and Pratt Whitney's geared turbofan architecture. Each carries its own strengths, risks, and advocates, and the final decision will not be made until the numbers are undeniable. For Rolls-Royce, the UltraFan represents its flagship bet on efficiency gains that remain inside a nacelle. The technology relies on a gear design with very large fan diameters, composite blades, and a variable pitch system. Rolls tested its first ground demonstrator in 2023, and a scaled version aimed at single-aisle applications is planned for test campaigns around 2028. Company officials note that they studied open rotor years ago, but their resources are now directed toward pushing UltraFan as a cleaner evolutionary step rather than a radical departure. Pratt Whitney, by contrast, has already fielded its geared turbofan on the A320 family and other narrowbodies. The company's message is simple: the architecture works, and further refinements can deliver the efficiency Airbus needs without the integration challenges posed by open rotors. From Pratt's perspective, the open fan may be chasing efficiency in theory, but the GTF has already proven itself in service with hundreds of aircraft. That track record is presented as a safer foundation for Airbus's next program. Across the Atlantic, Boeing has publicly expressed doubts about near-term open fan viability. While not dismissing the technology outright, reports suggest that its next single-aisle study leans toward a more traditional engine outline. The company appears unwilling to bet its core narrow-body franchise on a configuration that still faces unanswered questions about noise, certification, and integration. Inside Airbus, the official line has been cautious. CEO Guillaume Faury has acknowledged that open rotor efficiencies are promising but stressed that the jury is out on whether the concept is commercially viable. He has paired that with recognition of current challenges, including delivery delays with the CFM LEAP engines that already power the A320neo. That experience highlights the risks of tying Airbus's fortunes too closely to a single propulsion partner. Supplier arrangements are another key factor. If the open fan path proves viable, Airbus has signaled it could choose a sole supplier model with CFM that would give General Electric and Safran enormous leverage but simplify the program's supply chain. If, on the other hand, Airbus goes with a nacelle-based option, it could return to a dual-source approach, pitting Rolls-Royce and Pratt & Whitney against each other for market share. Airlines tend to favor dual sourcing for resilience and competition, so Airbus must weigh not only the engineering case, but also the commercial and political implications of its decision. For an open rotor to move from concept to service, it must clear a long list of certification hurdles. Safety sits at the top. Regulators require proof that unshrouded blades can be managed during failures. That means blade-off tests, ingestion trials for birds and ice, and demonstrations of stable behavior during fire, surge, or emergency shutdown. Integrating the engine with the airframe raises more questions. Large disc rotors under the wing demand altered wing geometry and longer landing gear, while aft mounting shifts loads onto the tail. Both options require control system tuning to cope with vibration and potential asymmetric thrust. Engineers must also design systems to remain segregated if a blade failure occurs. Noise is another decisive factor. Airports enforce strict limits at takeoff, climb, and crossover, and Airbus cannot sell the aircraft unless the sound profile fits within those boundaries. Work is underway on blade shaping, acoustic liners, and cabin isolation to address this, but the bar is high because the earlier prop fin experiments of the 1980s failed on acoustics. Practicality at the airport gate is also a constraint. Wider rotors expand wingspans, forcing Airbus to consider folding tips similar to the Boeing 777X. Without a workable solution, gate compatibility becomes a barrier no matter the efficiency gains. Finally, day-to-day operations have to be addressed. Open rotors change how crews perform inspections, how close ground staff can work, and what parts inventories are required. Training and manuals will need rewriting. The economics tie everything together. Airbus has to show that the promised 20% fuel savings hold up after accounting for heavier shielding, new wing structures, and altered maintenance costs. If the balance is positive, airlines will take notice. If not, the open rotor will remain a technology demonstrator rather than a production engine. Open rotor engines have been studied for decades. Concepts with exposed blades were explored as far back as the 1940s, but the real push came during the 1980s. High oil prices drove US and European manufacturers to test prop fin demonstrators. NASA worked with General Electric and McDonnell Douglas, while European teams ran parallel projects. Some of these engines flew on testbeds and proved they could deliver major fuel savings. The trials showed the physics worked, but they also exposed two barriers: noise and timing. The unshrouded blades created a harsh tonal signature that clashed with new airport noise rules. At the same time, oil prices collapsed in the late 1980s, erasing the economic case for further investment. By the early 1990s, prop fin research had been shelved, its promise set aside as airlines focused on quieter, conventional turbofans. That history still shapes the debate. Airlines and regulators remember why the earlier effort stalled, and it fuels skepticism that open rotors can be made viable. Airbus and CFM are now trying to prove that the tools of today, composite materials, digital simulations, and modern aeroacoustics, can solve the problems that engineers could not in the past. Composite blades can be larger and lighter without losing strength, while advanced shaping and damping target the tonal peaks that doomed earlier models. The difference in capability is striking. Analysts note that with computational fluid dynamics and precise rig testing, engineers can now map flows and noise sources in ways that were impossible 4 decades ago. Richard Abulafia summed it up by saying the older demonstrators look coal-powered compared to the current RISE test hardware. His point was less about style than about how much progress has been made in design tools and materials. Still, the past is a warning. This is not the first time open rotors have been labeled the next step in propulsion. If Airbus and CFM want to convince airlines, they need to prove that the efficiency gains outweigh the noise and integration penalties. The stakes are higher than before because the next single-aisle platform will anchor airline fleets for decades. That makes the credibility of the data, not just the concept, decisive. The open rotor effort now underway is more than a research exercise. Airbus and CFM are committing time, money, and credibility to prove whether this architecture can carry the next generation of single-aisle aircraft. The stakes are clear. If the data holds, it could reset economics and emissions in the largest segment of commercial aviation. If not, more conventional paths will take the lead. Either way, the decision will define the next decades of flying. For clear, detailed breakdowns of projects shaping aviation's future, subscribe to the channel and stay tuned for our next deep dive.